Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is capacitive complex impedance. Our objective is to learn how to represent capacitors as complex impedances for the purposes of AC circuit analysis. This lecture operates on the presumption the viewer has watched the resistive complex impedance lecture available at the Big Bad Tech channel. If you haven't watched this lecture yet or only dimly recall its contents, please take the time to do so now. You are no doubt familiar with the DC response of resistors, capacitors, and inductors. In summary, resistors follow Ohm's law, a phenomenon that relates voltage, current, and resistance. Resistors dissipate all power supplied to them in the form of heat and are not energy storage devices. Even our initial discussions of resistors and sinusoidal AC sources demonstrated that resistors consistently follow Ohm's law and voltage and current are in phase with one another. Capacitors and inductors, in contrast, are reactive elements and can momentarily store and return energy. As such, the reactive nature of these energy storage devices need to be accounted for. Recall from our discussions about the time-variant DC response of capacitors that initially uncharged capacitors experience a current spike followed by rising voltage. This behavior can be summarized as current leading voltage for capacitive elements, and that the current spike occurs before rising voltage. The time constant established by the capacitive circuit under inspection determines how slow or fast this exchange of energy occurs. Similarly, recall from our discussion on the time-variant DC response of inductors that inductors with no established magnetic field experience a voltage spike followed by rising current. This behavior can be summarized as current lagging voltage for inductive elements, and that the current rise occurs only after the voltage spike. As with capacitors, the time constant established by the inductive circuit under inspection determines how slow or fast this exchange of energy occurs. For purposes of time-variant DC analysis, we never really explored beyond these horizons. If, however, we push the boundaries into circuits incorporating sinusoidal AC sources that continuously change, there is no initial nor steady state, and reactive elements like capacitors and inductors will continuously store and discharge energy on a cyclical basis. Despite this constant interchange, one truth remains constant. Current will be in phase with voltage for purely resistive elements. Current will continuously lead voltage for purely capacitive elements, and current will continuously lag voltage for inductive elements. We'll examine this phase-shifted response in greater detail in later lectures. The reactive nature of elements in AC circuit analysis are accounted for using one of two tools. 1. Either time-consuming calculus-based techniques, or 2. Simple algebraic techniques making use of complex numbers. My choice is to employ complex numbers. Bottom line up front, resistors, capacitors, and inductors can be represented as complex impedances, where impedance is a term quasi-equivalent to resistance for the purposes of DC circuit analysis. Only the complex nature of impedance includes time-shifted effects for purposes of AC circuit analysis. The true nature of complex impedance will only become apparent in later lectures. However, we at least need to learn to calculate complex impedance for now. Resistors, when represented as complex impedances, are elements entirely in the positive horizontal real x-plane. Frequency of the AC source has no effect on the magnitude of the resistive complex impedance. As such, a resistor represented as a complex impedance can be calculated as the resistance value at an angle of 0 when represented using polar format. When depicted in the impedance domain, resistors exist solely on the real horizontal x-axis, proportional to the resistor's magnitude. If you wanted to represent resistive complex impedance using rectangular format, it would be proportional to R existing solely in the real horizontal x-axis plus or minus J times 0. Since we're representing the complex impedance of resistors using a complex number, note the value ZR includes an overbar, indicating this isn't just a magnitude, but also includes a direction. Capacitors, in contrast, when represented as complex impedances, are elements that exist entirely in the negative vertical imaginary y-axis. Frequency of the AC source does have effect on the magnitude of capacitive impedance using the following formula. Z of C, note the overbar, equals 1 over 2 pi times the frequency in units of hertz times the capacitance in units of farads at an angle of negative 90 degrees when represented using polar format. When depicted in the impedance domain, capacitors exist solely in the negative imaginary vertical y-axis, proportional to 1 over 2 pi Fc. We'll examine capacitive complex impedance in detail in today's lecture. Finally, inductors, when represented as complex impedances, are elements that exist entirely in the positive vertical imaginary y-axis. Frequency of the AC source does have effect on the magnitude of inductive impedance using the following formula. Z of L, note the overbar, equals 2 pi times the frequency in units of hertz times the inductance in units of henries at an angle of positive 90 degrees when represented using polar format. When depicted in the impedance domain, inductors exist solely in the positive imaginary vertical y-axis, proportional to 2 pi FL. We'll examine inductive complex impedance in an upcoming lecture. You'll note the units of complex impedance, regardless of the resistive, capacitive, or inductive nature of the element in question, are always expressed in units of ohms. Only direction gives some clue as to the resistive, capacitive, or inductive characteristics. Purely resistive elements have a magnitude in units of ohms proportional to R at an angle of 0. Purely capacitive elements have a magnitude in units of ohms proportional to 1 over 2 pi Fc at an angle of negative 90 degrees. Purely inductive elements have a magnitude in units of ohms proportional to 2 pi FL at an angle of positive 90 degrees. Additionally, note capacitors and inductors are essentially mirror images of one another, with a 180-degree differential between them, a fact we'll use to our advantage in industrial applications like power factor correction in later lectures. As an illustrated example of application of the capacitive complex impedance formula, consider a 22 microfarad capacitor subjected to sinusoidal AC with a frequency of 60 Hz. Let's calculate the complex impedance of this capacitor, expressing our final answer using polar format. By all means, follow along and see if you can obtain the same values I do. By the way, this isn't a polite suggestion. Pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. When we substitute our given values into the capacitive complex impedance formula, we arrive at an impedance value of 120.6 ohms at an angle of negative 90 degrees. When calculating capacitive complex impedance, don't worry about the angle at first. Just calculate the magnitude using the formula 1 over 2 pi Fc and stick at an angle of negative 90 degrees behind it and call it good. If we were to express this in rectangular format, Z of C would be equal to negative J 120.6 ohms. Although equivalent, rectangular format is somewhat old-fashioned. All the cool kids nowadays are using polar format, and I suggest you do the same if you want to stay on the cool side of history. By the way, if you're getting a different magnitude than I am, remember the scientific calculator follows the order of operations exactly as entered and does not take into account what you meant to enter. As such, it's often necessary to enclose the term below the division operator, 2 pi Fc, in parentheses, to make certain the scientific calculator executes the formula exactly as you intended. Introductory AC circuit analysis scenarios largely involve use of this basic impedance formula. As such, let's gain some practice using it with some example problems. First problem, what happens to the capacitive complex impedance of this 22 microfarad capacitor if I double the frequency to 120 Hz? No calculations, just think about it. Does the magnitude and direction of the respective complex impedance decrease, increase, or remain the same? Take the batteries out of your scientific calculator and put it on the table and put your hands in the air. Just look at the formula and answer the question. What happens to the capacitive complex impedance of this 22 microfarad capacitor if I double the frequency to 120 Hz? Does the magnitude and direction of the complex impedance decrease, increase, or remain the same? By all means, pause the lecture and think about this. But don't you dare touch your calculator because I'm watching you.